Good morning, mathematicians. How we doing today? I'm kind of tired. Yeah. I gotta make, I remember a couple months ago when I was still putting out the occasional longer video, my subscriber list was slowly climbing. Now it is really slowly climbing. Yeah. I gotta make more content, yo.
I remember.
But I have work to do. I mean, these things are in conflict. I do have a video or two I do want to make soon. You know, one thing I got stuck on. I wanted to keep going with my rings and modules series, or categories of modules. I mean, I could just skip ahead. There's so much more to say, but I got stuck on this one result, proving, I think it was like associativity of the internally defined addition of an additive category. Yeah. Yeah, for some reason, that one was tricky. And then I spent too much time on it, and I just, like... Yeah, I'm like, well, I gotta work on other things. Would I happen to know anything about the construction of a full subcategory in a large category? Suppose. I mean, I know examples of that, but I don't know... I don't know what exactly you mean by the construction of a full subcategory in a large category. Because it's not like... yeah, I mean, it's not like there's an algorithmic procedure. I mean, really, you just pick, so, like, it basically just amounts to picking some collection of objects. You just pick a sub-collection of objects, and you take all the maps between them. And that's pretty much it. Yeah. So, I mean, as an analogy, let's consider a graph. So let's say this is our graph. And, like, a subgraph of the graph could be something like this. You could just take some of the edges between them, right? And some of the vertices. But this would... Right. And we could also say take this vertex and neglect to take these other edges. So an induced subgraph... So this is a subgraph, but it's not an induced subgraph. An induced subgraph says if you have any two vertices, you must take whatever edges, or any vertex. You must have the edges that are incident with it in the parent graph. So this is completely analogous to the setting of a full subcategory. Are there substantial differences between constructing a full subcategory in a small category versus a large category? I see. One second, let me just address the other comments. So Arad, actually I didn't have office hours yesterday. The last few office hours, what have I been doing? Well, hey, I mean, you can always go catch up with the recordings. But the time before, I was ranting about something I'm stuck on with exceptional pullback of some perverse sheaves. And yeah. Today I'm planning on doing some heck algebra computations, which I might have done before, but I don't know. Take care of your mental health, almost prof, almost quant. Yeah. So we have free math from you for a few decades, yeah. For many decades. Yeah, so anyways, I think fractal computer, I think the answer is really no. Yeah, the answer is no, because again, it just amounts to picking. In the end, it just amounts to picking some sub collection of objects. So now, whether that sub collection is hello Lola, whether that sub collection is large or small, I mean, I guess there is a difference there, and there are set theoretic things you should be careful of, but if it just comes to the bare existence of a small category versus a large category, I don't think there's anything. Or I mean, the full subcategory, I don't think there's anything to really you need to be too mindful of. Like, if we consider the say category of finite dimensional real vector spaces, of course one could take one could take the full subcategory where you just take all of the Euclidean spaces. And this would then be a small full subcategory. Or you could take the subcategory of all one-dimensional one-dimensional vector spaces, take the full subcategory generated by those, and then that itself would be large, right? But yeah, I don't see it like you could just do whatever. I don't think there's much issue. Like, if you run into an issue, I don't know, like if you're doing something that says, oh, suppose this category is small or something, then blah, blah, blah. Okay, then maybe you need to be mindful if you're applying one of those results. But you're reading through one paper by Lurie and got curious. There might be differences between particular small, large constructions. I mean, definitely there are places where you need to be mindful of set theoretic conditions. But I think when it comes to just the bare concept of full subcategories, I really don't think there's much to worry about. I don't know to what extent I agree with your comment, Rad, because I mean these like, I don't know, these things aren't so easily disentangled. People like to talk about like these are very different things, but like, yeah, I don't know, all category theory. Okay, there's these proposals for sort of purely category theoretic descriptions of the category of sets or something. You take that as axiomatically, but nonetheless, size issues exist everywhere. I mean, this is like on Land's book on infinity categories. The very first page is like, okay, we choose a Grothendieck universe, and sure, you just toss it aside, and it's you don't really care about it. It's just some formality you need to make sure everything, you wave your wand of incantation and make sure everything works, but like, it does need to be said. So, yeah. Yeah. Okay, so here's a computation I kind of want to do just for myself anyways, for research related purposes. Well, this is, I don't know, a very simple case, but I want to compute some stuff. So I want to compute in particular, let's look at the case when I have a character of the rank 2 torus over a p-adic field. In particular, the character I have in mind is this one. And it should be the case that when I induce that character, I take normalized parabolic induction of that character. I get an indecomposable representation of length 2. The trivial representation is a sub-representation, and then when you quotient by that, you get this infinite dimensional representation, irreducible representation called the Steinberg representation. But now I want to approach this through the theory of Hecke algebras. And so it should be the case that normalized parabolic induction agrees with, so if I took this and then say I took the I fixed points of everything, meaning the Iwahori subgroup, and I considered the modules given over the Iwahori Hecke algebra, which is isomorphic to the affine Hecke algebra, say of size 2, then it should be the case that this is the same, and maybe, I don't know, like GL2 this should be, of tensoring over the torus, taking the module corresponding to the character of the torus, but then also, if I understand correctly, according to one source of music, there's a whole bunch of, the literature is all over the place on the different incarnations of the Hecke algebra and categorical equivalences used. But then this should be the longest element of the Weil group, which basically for us is just represented by this matrix in GL2. Hey, Tenacity, been a while. Yeah. Okay. So I want to do this computation in two different ways. First, I want to compute. Well, let me do this computation. No, let me do this computation first, because this one should be easier. I just want to make sure everything lines up. So, like, the Hecke algebra should be generated by functions where this is the this should just be the characteristic function of I, Wi, and well, it gets a little more complicated for these other words. How do I say this? Maybe I should jump ahead. It turns out these TWs, TW should just act for the trivial representation. It should just act by Q, and now should I explain why this is true? Yes. So okay, let me just explain why it's true. And I'll explain what this is supposed to mean as well. Have I ever encountered moduli spaces in my studies or research? Yeah, certainly. I mean, the varieties that I work with can be thought of as a coarse moduli space of Langlands parameters. Yeah, so in a sense, I work with some moduli spaces. I mean, I have some very old videos on the geometry of SL2Z, which are also like coarse moduli spaces for complex elliptic curves. There's also, yeah, I mean, the categorical local Langlands people deal with the moduli stack of Langlands parameters, so you glue all of these spaces together in some big stacky way. And then, yeah, of course, you know, I've enjoyed reading a bit about stacks and the whatnot, and you get moduli stacks of elliptic curves and whatnot out of that. Though I wouldn't claim any expertise on these topics, certainly. Certainly not. What's a Langlands parameter? That is a good question. A Langlands parameter is so first it's a homomorphism. In short, it's a homomorphism from the Weil group of a p-adic field to the L group of some group. Well, okay, so first off, there's Langlands parameters for real, complex, and p-adic groups. But, okay, in short, a Langlands parameter is just a homomorphism of groups. It's a special kind of homomorphism of groups. Okay, but it needs to be continuous, and it needs to satisfy something called Frobenius semi-simplicity. And also, what the hell even are these groups? So, okay, let's unpack what these groups are a little bit. Thanks to my video, you could understand better Anna's talk at IAS on Langlands. Oh, I don't know if I know that one. Maybe I'll pull it up on my second laptop here. To remind myself to look it up later. Wait, which one of my videos? I guess one of my Langlands ones, probably. A glimpse into the Langlands program. 1 year ago. Okay. We'll put that in pause. Maybe I'll watch that later. Oh, there's a two-parter. Two-parter at least. Okay. Oh, and my video is the classic SL2 action on H. Oh, those are... oh, okay. Cool. I would have assumed it was one of my videos that are like introduction to the Langlands program or something. So, okay, let's talk about Langlands parameters. So, what does the Weil group look like? Well, the Weil group is basically, I believe it's a dense subgroup of the Galois group of the closure of F over F. Well, New Wave Infantry, we got one question at a time. This question will take the rest of the office hour to answer. What's a very, very rough idea of geometric Langlands versus categorical versus local? Are there more? Yeah, I mean, there's like global Langlands. There's a whole bunch of Langlands. I mean, geometric Langlands, very roughly, those are basically, you're looking at groups over function fields. Local Langlands is looking at groups over local fields. So function fields are, things like, the functions of some algebraic variety. So there's function fields, then there's local fields, which are like R, C, and QP. And then like global Langlands is sort of like the one that we're really after, that we're really interested in. I guess roughly those cover the main things of Langlands. I mean, and each one of these basically people are trying to categorify, in the sense that, like, the original Langlands correspondence is basically just like it's this bijection that's expected to satisfy a whole bunch of nice properties, right? And it's like, oftentimes when there's some meaningful way to map between one thing to another, that's sort of most nicely codified with the existence of a functor, and especially if there's supposed to be some equivalent perspective between two things, there should be some sort of equivalence of categories. So very roughly, people are trying to bump everything up to an equivalence of categories, which is proving to be difficult and really cakes on many layers of abstraction. But I mean, it seems to be working out. So you really want to get into a Ph.D. program, but you feel you're not good enough for mathematics. You got a BS in all your math courses, and one more year left of undergrad. Any advice? Well, I guess you don't. I mean, why do you think you're not good enough for mathematics? Got to take an evidence-based approach. There's really only one way to know if you're good enough for mathematics or not, and that's to give it an honest try. Also, what does it mean to be good enough for mathematics? I mean, yeah, do you want to be a tenured prof at Harvard, or do you want to teach at a community college in the middle of nowhere? Both of those things, you could be a mathematician and do those things. Or do you want to make like $40 million a second on the stock market? Or do you want to like help hack computers? I mean, yeah. So it depends. It depends on what you mean good enough for mathematics. So first off, I mean, mathematics itself could be stratified into many tiers. So yeah, I mean, how did you do on your courses? And have you done any research? And how did that feel? Yeah, because like there are things to be mindful of. Like realistically, mathematics is a tough grind, and the job market. I mean, everyone's job market is taking a hit right now, but like the mathematical job market has been very not. It's been difficult for a long time, and I don't think it's going to get any better. So, yeah, I mean, if you want to be a tenured prof at Stanford in a research-only position, well, temper your expectations because, like, understand that is a hard thing. And that also the path to being a mathematician, could be in conflict with other goals that you have. I mean, I'm pretty happy where my life is, I would say. Actually, I wish I was less poor and could afford to live on my own right now. But, for example, like I'm 33 and if I do stay in academia, I've still got a few years to go through the postdoc grind. And if, for example, that wouldn't really be compatible if I wanted to start a family in the next couple of years. I mean, I should say, people do it. People have families during their PhD and stuff all the time. But, I couldn't imagine doing that on top of my life right now. So, yeah. I mean, you have a lot of passion for math, and you want to do research and one day publish papers. So, I honestly look 24. Well, that's the magic of the camera. Also, I work out a lot, and I get a lot of cardiovascular exercise, and I try to eat as healthily as possible, avoiding high-processed food, blah, 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 skincare routine, blah, blah, blah. So that's probably has something to do with it. But yeah, even if your goal is to publish research, I mean, that can look like so many different ways, and there's yeah, there's a million different ways that could look. You don't need to, like, people do publish. I mean, it's more rare, but people, do publish in not terrible journals who are not professional mathematicians, although probably have had some professional training, like an undergrad. Yeah. Okay, now I'm just rambling. I should go back and answer the questions. How many kilograms do I squat? I've stopped squatting recently because it just wrecks me. I find, especially when I'm going hard. But I think before I was doing maybe like 150 for like 5 sets of 10-ish. No, that's probably a little more than what I was doing at the peak. But I did the leg press. What did I do? Leg press the other day. I have actually. Let me show you. So, because in order to make progress, you should track everything. I've got Excel on my phone, and both for my diet to calculate my daily caloric intake and protein intake. I track everything on my phone, and so you can see. Maybe you can see I've got all these numbers on my phone. I track all my exercises, the weight, the number of reps for everything. So what did I do? Yesterday, I did the leg press, 290, 4 sets of 12 at 290, and then 1 set of... I didn't say how much I did. I think it was 12 at 300. So that's my leg game. I think my leg game's pretty good. I'm pretty happy with it. Anyways, enough about my workout routine. Some math. Desen was told that gal Q bar over Q is hard to study. Is this one of the many settings where the particular Galois group can be studied? Well, yes. So getting back to the other versions of like global Langlands is our ultimate goal. Like, we want to study this. We want to study gal Q bar over Q. And it's a hard group to study. Of course, studying groups is made easier by studying representations of those groups. And very roughly, Langlands says that automorphic reps should correspond to Galois reps. So that's this is kind of one of the reasons why Langlands matters. Is ultimately we want to understand this group to understand number theory. That becomes, say, easier if we understand Galois representations, and the conjecture says, well, that can sort of be probed with automorphic representations. So, the correspondences that exist should allow us to, say, perform operations on automorphic representations, which gives us corresponding operations here, and we should be able to push information back and forth across this correspondence. Yeah. And so, so that's a good question. What would be the V group for that? Well, ultimately, I mean, this is, let me just look at the other comments. We'll probably yap about this for a bit, but Langland's holy grail of studying such Galois groups, exactly, yeah, because it tells everything about the representation theory, yeah. Fractal computer just wants to understand shit. Yeah, me too. Me too. But I also want to live on my own. So I need more money. You have a lot of... Oh yeah, I went over that. Want to teach kids for free and live poor for the rest of all your life. I mean, that's great. I would do some free teaching for kids too, I suppose. But yeah, I mean, be open to the possibility that you'll be sick of being poor your whole life. Because I thought I didn't care. And sometimes your mind can change on topics you never thought it would. Anyways, getting back to these Galois representations. So yeah, let me answer. There isn't really a need for a V group here, necessarily. Well, actually, there is a need for a global L group. Okay, complicated things, but let's get back to the V group, the local V group for a second. So this is over local fields where we have a much better understanding of the Galois group. This is Gal QP bar over Gal QP, right? If F is QP, for example. So the V group is formed. I hope I don't say anything wrong, but it's something like this. You basically take an exact sequence. So you look at there's for each extension of degree n, there's a unique unramified unramified extension of QP of that degree. So something like this. And you get an exact sequence of groups. You get an exact sequence of groups here. This is called the inertia group. Maybe this would be the inertia group of F over QP, say. And then basically you take an inverse limit of this sequence. And so you get the Galois group here, which is ZP. And you get some, like, this is like the unramified limit of the unramified extensions, and you get IF. And then you, so this is the limit. This is the limit of these inertia groups. And then this is sort of, there's a copy of the integers in here. And you basically take the inverse image of 1, and you look at the group generated by the inverse image of the identity here. And basically, well, this should be generated, let me say this. So in each of these groups, we have a Frobenius automorphism, right? So in this limit, we can take a choice of Frobenius, by which I mean it's the automorphism that restricts to the Frobenius automorphism for every P. And then Arad, I don't know if that's an intentional pun. I suspect it is. This inertia stuff sounds wild. Because there's like tamely ramified wild ramification that all has to do with the inertia group. But so basically the Val group is generated by these inertia groups, and or the V group, sorry, is generated by this inertia group and this Frobenius element. So maybe this isn't so helpful, and but okay, we're getting closer to like, well, why is that right? Like the global side, you would think, oh, we're looking at Galois representations. On the local side, you'd think, well, shouldn't we also be looking at Galois representations? Well, guess what? It turns out, here's maybe a more enlightening fact. It turns out that, say, if we have some finite extension of p-adic fields, then the V group of E is contained in the Vega group of F, and in fact we have an isomorphism from the quotient to the Galois group of E over F. So, yeah, this is step one, I guess. Now what? So let's say we wanted to probe. Let's say we wanted to probe Galois representations, these finite Galois representations. Well, we can do that, and so basically, what you do is you start by taking a representation of your Galois group. So again, this is just a finite Galois extension of p-adic fields. Take some irreducible representation, and now you can pull it back to the Vega group, right? You just take the composition of the quotient and the isomorphism with sigma, and then using some abusive notation, we can basically just write sigma for a representation of the Vega group. So we would call this a representation of Galois type. Right? And now that the L group stuff I mentioned above is maybe a little well, we need this in full generality, but if we drop the L for a second, so well, let me say something over here. More specifically, say like in the global Langlands case, more specifically, if we have automorphic representations of GLN over the Adels, those should line up with the n-dimensional Galois representations. So in the same way, more specifically, if this is a representation of Galois type, then really, well, mind you, I guess I haven't even started talking about the Langlands correspondence. So you should imagine that this should line up with representations of GLN QP, right, and n-dimensional representation here, or GLNF, whatever, GLNF, yeah, right. So yeah, so this is part of this is not the general definition of a Langlands parameter, but this is one example. This is a Langlands parameter. So it's a representation, but it's a Langlands parameter of Galois type. Yeah, Dason, there's also, I think a good thing to accompany this would be, what is it? There's this, by Knapp, there's an introduction to the Langlands program, and he talks a bit about how you construct the Vega group and stuff through this, like, taking limits in this exact sequence. Yeah, there's also a good article by Rohrlich on, like, it's like elliptic curves and the Vega and representations of the Vega group. Yeah, so that's worth checking out. So now you've probably heard the slogan, possibly, that the Langlands program, the one-dimensional Langlands program, is class field theory. So, of course, just like there's global and local Langlands, there's global and local class field theory. And so local class field theory basically tells you that, yes, the Buzzard lectures are also very good on YouTube. Good recommendation. So what are all the one-dimensional representations? There should be a bijection between so GL1 of F, right? That's just F cross. So its representations. So irreducible representations of this should be a correspondence between these and irreducible representations of the V group. Yeah. Mind you, yeah. So right. So this is a kind of Langlands parameter, but actually, whoa, everything that was here before disappeared. Oh, it's just freezing. There we go. I should say that technically what I said, this is part of the data of a Langlands parameter, but this is more closely, since it's just of the V group, this is more closely what I would call an infinitesimal parameter. Whereas a Langlands parameter, more generally, we're going to need to beef this up. Well, there's two perspectives on it. It's either you take the V group and a semi-direct product with C, or equivalently, you could take the V group and just a Cartesian product with SL2C. And we're going to see that we'll need to bump this up. But actually, I have to go, because I have to go, I have to give a quiz. I have to deliver a quiz to some students, stand around and watch students take a quiz. Yeah, but I guess we'll maybe continue with this stuff soon, and or switch over to heck algebras. But yeah, probably tomorrow I'll talk about some of this stuff again. So, all right, go